So you guys have started classes and such already.
Yeah, 4 weeks ago.
Oh, I see. I see. I think we don't start until like 2 or 3 weeks from now. So
Yeah,
that's it's a very big difference of
yeah. Maybe that's why Song can still be traveling
yeah, yeah,
this time.
exactly. Yeah.
And he told me your semesters are pretty short, only 9 weeks.
9 weeks. Yeah, it's even shorter than the usual quarter system is 10 weeks, but here it's
Oh.
nine for some reason. Yeah. Yeah. Must be hard on the students.
Mhm. Oh, by the way, do you want to share the screen now?
Ah, yeah. Let me do that. Um, is it working? Can you see the screen?
Yes, I can see the screen. I can see the cursor. I can see the tackle.
Okay, great. Perfect.
Maybe let's just wait for 1 more minute.
Yeah.
Those three papers were out in July. So many papers were out in July.
Yeah, we all put it out on the same day. Yeah, it's a little bit, yeah, hectic.
I mean, there were also many other papers, interesting papers during July.
I see. I see.
Mm, maybe we can get started. Are you ready?
Yeah. Yeah.
Let me record.
Recording in progress.
Good morning, everyone. Welcome to the Condensed Matter seminar series. It's my great pleasure to have Marvin Chi as our speaker today. Marvin graduated from University of Colorado Boulder last year, I think, and now Marvin is a new postdoc at the University of Chicago. During his PhD study and postdoc study, Marvin has already done a wide range of research, ranging from fractons, parameterized topological systems, and also hydrodynamics. And today he's telling us about uh, mixed state topological phases.
Yeah. Thanks so much, Sujin, for the introduction and for the invitation as well to give this talk. So yeah, today I'll be happy to tell everybody about this gadget that we'll call the Symmetry Taco, and we'll use it to describe some kinds of equivalences, roughly speaking, between gapless, gapped, and mixed state SPTs. So the Symmetry Taco, yeah, it'll be a sort of extension of the SymTFT framework to mixed states. And so this talk is based on this archive posting, and we put it out at the same time as with two other groups on the same topic on the same day. Um, so yeah, I couldn't have sort of done this without the help of my collaborators, Raman, Xie, David, and Abhinav. So I'm very grateful for for working with them. So yeah, I'd like to just take a step back first and pontificate a little bit about gapped phases of matter. So in some sense, gapped phases are the simplest kinds of possible phases of matter, but already actually they're able to exhibit quite a wide range of phenomena. So I've drawn like a cartoon map of some of kinds of phases that some kinds of gapped phases that people like to study. So to begin with, there's the trivial insulator, which is essentially just featureless at low energies. There's an energy gap, and it's featureless, below that energy scale. On the other hand, we could have symmetry breaking phases. These are characterized by a symmetry enforced ground state degeneracy and a local order parameter. Um, so moving on, we have SPT phases. These are very similar to trivial phases in some sense. They're also featureless insulators in the bulk, but they're actually kind of distinct in a topological sense from trivial phases due to the presence of non-trivial kind of low energy degrees of freedom at the boundary. These are typically what people call edge modes, and they manifest like a topological distinction between between the SPTs and the trivial state. And finally, there's a slightly different class of gap phases known as topological orders. These are they have non-trivial, topologically protected ground state degeneracy. When I put them on a non-trivial manifold, they have anyons, long-range entanglement, and all that. And so, yeah, gap phases, encompass these and sort of many other types of classes of phases of matter. The one thing I want to draw people's attention to is actually this recent idea that's emerged over the last 10 years or so, which is that actually topological order has a lot to say about these other types of phases. And in particular, this is this notion of SymTFT, the SymTFT construction, which people often represent or talk about it as a sandwich. And the SymTFT kind of perspective gives insights onto these other types of phases of matter. And I'll elaborate more on this in a few slides. The other thing that I'd like to just kind of explore briefly before getting into the main talk is this idea of fractionalization, which is one of the really, really striking kinds of emergent phenomena that can happen in gap phases. So the idea, obviously, is that there are some situations in which the low energy degrees of freedom that are excited when I probe the system can be, in some sense, fractions of whatever my microscopic degrees of freedom are. Probably the most striking example of this is in the fractional quantum Hall effect, where if I take an electron and I inject into the system, I actually see 3 quasiparticles, each with a fractional charge of 1/3 of the electron. And this is a emergent property in the sense that if I only have a few electrons, I'm never going to see this. But as soon as I have macroscopically many, this is possible. Another kind of class of fractionalization that people are able to observe in systems are the kinds that can be pictorially drawn in this manner. So this sort of describes a cartoon description of many kinds of systems. For example, polyacetylene or the Majorana wire or the Haldane chain. Their unifying feature is that at a domain wall or at a boundary between 2 different phases, I have these dangling edge modes. So this is like the SPT type of fractionalization that we talked about on the previous slide. And yeah, and this is another kind of fractionalization that can happen in gapped phases. Another sort of realization that has emerged over the last few years is that some fractionalization patterns are impossible to realize in gap phases, but they can be once we move beyond that setting and consider gapless states or mixed states. And this generalization, or being able to find different fractionalization patterns when you sort of go beyond gap states, is really a motivation to try to understand the SymTFT tool that we have in this broader setting. So there has been some work over the last few years about how to understand gapless SPTs using the SymTFT tool. I actually understand Rui Wen gave a talk earlier this year, I believe, just at this seminar series. So to the experts, I apologize. I'm going to be repeating some of that material. But the rest of this talk will also discuss how the SymTFT perspective can be extended to mixed states as well. Okay, so yeah, just a brief outline of what I want to be talking about. So first, I'll review SymTFT both in the very well-established setting of gapped phases and in this newer setting of gapless phases. Then I'll describe a method or a conceptual way to relate gapless SPTs and gapped SPTs using this SymTFT tool. Then I'll kind of digress for a little bit and talk about mixed states. I want to get to mixed state SPTs and how they're related to gapless and gapped SPTs via SymTFT. And finally, I want to use SymTFT to use this perspective to discuss what's called gauging of a weak symmetry. So I'll discuss that. I'll discuss that later. Okay. So yeah, let me just give a kind of quick overview of this SymTFT picture for gap phases. I've included here a very incomplete list of people who have contributed to our understanding over the past 10 years or so. Um, so the rough picture is the following. I want to consider a 1D lattice model, so very microscopic data. And I want to kind of zoom out, imagine zooming out and, or in a sense, doing RG, and try to extract the universal data of the phase. And the kind of central claim of the SymTFT picture is that the universal data in this 1D lattice model is actually holographically encoded in this in a two-dimensional topological order. So just to be like a little bit more concrete, for a 1D lattice model, I'm imagining a 1D chain of qubits, for example. They could be any sort of degree of freedom. And let me impose a Z2 symmetry, which acts as spin flips on these degrees of freedom. So the claim is that this data, the symmetry data, and the data encoding gap phases is can be sort of repackaged into this kind of picture, where this 2D topological order that I want to consider is the Z2 toric code, Z2 because I want to consider Z2 symmetry. And importantly, this Z2 toric code is kind of defined on a slab. It's defined on a slab that's finite in one direction. So this is really trying to capture the data of a 1D lattice model. Okay, and the slab has two boundaries. So I've labeled one of them as the so-called symmetry boundary and the other as the dynamical boundary. The symmetry boundary characterizes or encodes all of the data about the symmetry of the system. And for this construction, the symmetry boundary will always be charge condensed. So the Z2 toric code has both an E anion and an M anion. Charge condensed means that the E is condensed. The dynamical boundary, while we're in this setting of gapped phases, the dynamical boundary will be any gapped boundary of the system, and the choice will sort of reflect the phase of matter of my 1D system. And yeah, please stop me if there's any questions as well. Yeah. Okay, so I've said that
Excuse
the
me, sorry.
SymTFT is supposed to characterize
Excuse me.
the universal properties of the phase. So let me focus on for now, the coarsest property, which is the ground state degeneracy. So let me start with the
Marvin,
paramagnetic. Yeah.
Marvin, I think there was a question.
Oh, sorry. Yeah.
Excuse me. So can you hear me?
Yeah.
Oh, so you said that the dynamical boundary should be the gap boundary of the system. So for toric code, I think there are only two choices.
That's right. There's only two choices.
Okay, thank you.
Yeah. Okay, so yeah, let me focus on the paramagnets for now. And so for the paramagnet, the choice corresponding to the paramagnet is for M to be condensed on the dynamical boundary. So yeah, in this picture of the toric code, the bottom boundary I've denoted as the symmetry boundary, and now on the top boundary, the dynamical boundary, I've condensed M. And yeah, it's for those familiar, it's quite easy to show that the Z2 toric code has a ground state degeneracy of 1 with these boundary conditions, which is it's a good sign. We know that the Ising paramagnet has a ground state degeneracy of 1. And yeah, and one feature of this picture is that, for example, if I act on the Z2 toric code with the M string operator, this M line operator, I can push it to the top boundary, which means that the M string kind of acts trivially on the system. Okay, so that's the meaning of this line. We'll come back to that later. On the other hand, if I consider the ferromagnet Hamiltonian, this corresponds to condensing E on the dynamical boundary. And similarly, yeah, now the bottom and top boundaries both E condensed. And because E is condensed on the top and bottom, I now have access to a local operator theory, which physically corresponds to E tunneling from the top and bottom. And this local operator anti-commutes with this M string that I introduced in the previous slide. And so it's very, very natural to identify these two operators with the order parameter of the original Ising model and the symmetry operator acting on the entire system. And indeed, because these two operators anti-commute, the Z2 toric code with these types of boundary conditions has a ground state degeneracy of 2. And of course, this reflects the twofold degeneracy in the ferromagnet case. The other kind of universal piece of data in the Ising model is the behavior of the order and disorder parameters. So in the Ising model case, in the paramagnet case, for example, if I act with the M string operator, I can kind of push it up to the boundary and it acts trivially. But another way to say that is that this disorder parameter where I take X, a long string of X's, this will act trivially on the state. And of course, this reproduces the expected behavior of the disordered phase of the Ising model. On the other hand, if I'm working in the ferromagnet phase, again, I have E condensed. I can act with these operators, which act trivially on the system because I can push the E's to the boundaries. And then I can reconnect these two legs to get an operator that looks like this. And using the identification that we talked about before, these E tunneling operators are essentially like the local order parameter of the system. What we find is that the local operator acting on one side and the other side, there's long range order in the local order parameter. Again, this reproduces everything we know about the Ising model.
Question?
Yeah.
In the previous page, for the paramagnetic phase, suppose I push the blue line to the E condensed boundary.
Yeah.
Then it's supposed to be short-range correlated.
No, yeah. So the way to read the picture is that yeah, you can kind of think of these operators as acting in the low energy subspace of the toric code. In which case, if I act if I act with the M string operator in the low energy subspace, it acts trivially. And the way to see that it acts trivially is that I can push it up to the top boundary.
But if I push it to the bottom boundary, what happens? It's not in the low energy space anymore.
If I push it to the bottom boundary, its action is equivalent to as if I pushed it on the top boundary. And we know that, and because I can just disappear it on the top boundary, the action is the same. Sorry, that it acts as the identity. The point is that, yeah, because when I'm in the low energy subspace, I can wiggle this line however I want in the low energy subspace. And so if I push it down, I'm allowed to do that. If I push it up, I see that the action is trivial. So the action will be trivial no matter where this line is.
In the bulk and in the top boundary, I understand, but in the bottom boundary, why is this obvious? If I push the entire blue line on the E condensed boundary.
Yeah, so basically, if I try to push it down to the E condensed boundary, I can't absorb the line, so it's always there. If it's there, I can wiggle it. It's topological, right? So I can wiggle it however I want, and I can move it to the top boundary.
I see.
Yeah. Yeah, the point is I can't absorb it at the bottom boundary. Yeah. Yeah, thanks for the question. Great. So that sort of concludes the review for the.
Can I
Yeah.
just make sure then? If I just view this thin slab as a 1D system, because it has a finite width in one direction and infinite length in the other direction, I should really view it as a 1D system.
That's right.
Then does this picture predict the existence of something like the E condensed boundary in any 1D Z2 paramagnet? What is that?
Does it predict the existence of an E condensed boundary?
In the language of a pure one-dimensional system, what does this E condensed boundary mean?
In the language of the pure 1D system, the E condensed boundary corresponds to symmetry breaking. So indeed, for any kind of symmetry, there will always exist a symmetry broken phase. Yeah.
But I'm looking at the paramagnetic phase, and I'm looking at precisely the picture here.
Sorry, you're asking about the E condensed boundary at the bottom.
Yeah, I view this as a 1D system.
Yeah, so I would say when you view this as a 1D system, the E condensed boundary on the bottom together with the M condensed boundary on the top tells you that you're in a paramagnet. If I don't specify anything about the top, all I can say is that all I can say about given the data of the bottom boundary, all I can say is that I have a Z2 symmetry.
Mm-hmm.
Yeah, you can say it's like a kind of a convention for E condensed to appear on the bottom
Uh-huh. Mm-hmm. So the existence of these E-condensed boundaries in a purely 1D system just means there's a Z2 symmetry.
That's right.
Mm-hmm. Thanks.
Yeah. Okay, so to move on to a slightly more non-trivial example, I want to discuss the kind of paradigmatic example of a 1D SPT, which is known as the cluster state, and how it fits into the SymTFT framework. So the cluster state is a model where I have 2 qubits per unit cell. I can think of it as being qubits living on even and odd sites. And there's 2 symmetries, which are spin flips on even and odd sites, or the A and B sublattices. And the Hamiltonian is I've written it like this, but I'm sure many of you have seen it in the form where it's like ZXZ on neighboring qubits and ZXZ on neighboring qubits. But I've written it this way and color coded it this way to make the correspondence with the SymTFT a little bit easier. So I'll just say that yeah, so if I want to make the correspondence with SymTFT, because I'm trying to describe a system with a Z2 times Z2 symmetry, the uh, the topological order is the Z2 times Z2 toric code. Again, on the symmetry boundary, I've condensed the charges of the symmetry. And in order to describe the cluster state, I have to choose a particular dynamical boundary. And the dynamical boundary that I've chosen to reproduce the cluster state is where EAMB and EBMA are condensed. Okay, so I won't reproduce all of the physics of the cluster state here, but I just want to say something about the string order parameter, which in some sense, is everything there is about the cluster state. I think everything can be sort of derived from the behavior of the order parameter. So playing kind of a similar game to what we've been doing on the previous slide, we can identify this type of string order parameter as acting trivially on the ground state. And what this means, you can identify this combination of string operators as acting trivially on the ground state. And so when you translate that back into qubit language, what you find is that this means that this type of string order parameter is long range ordered. And this is the characteristic, you could say defining feature of the cluster state SPT. One thing to notice is that the endpoint of the string order parameter carries a symmetry charge. So the endpoint of the string operator is ZB. It's charged under XA. Sorry, it's charged under XB. And this is kind of the notion, this is where fractionalization in this system comes from. So from the behavior of this long range order of this string order parameter, for example, I won't do so here, but you can derive for example, the presence of edge states and so on. Okay, are there any questions about the cluster state case?
I have a
Okay.
question.
Yeah.
So, in some of the 1D SPT, it cannot be detected by the standard string order parameter.
Yes.
Then for those SPTs, how does this picture work?
Okay. Yeah. So let me first say that for any abelian SPT, I think they're all detected by string order parameters. The complicated ones, like the ones that you mentioned, all have some kind of non-abelian symmetry group. And what happens in the non-abelian case is that I cannot just specify the boundary by saying which anyons are condensed. So in fact, there's additional data when I'm in the non-abelian setting for in order to specify a gap boundary, I cannot just say what the anyons condensed at the boundary are. I need to specify some extra data. And I believe it's like kind of in this specification of extra data. Yeah, it's like the fact that the anyons themselves don't contain all the information, I think is what leads to the string order parameter not containing all the information.
I see. But hopefully, after specifying the extra data, I will be able to specify the SPT information even in those cases.
Yes, yes. So yeah, I'm not actually sure what is the right thing to look for in those cases.
You mean
Yeah.
what do
Yeah,
you
I'm
mean
not
by
actually sure what the distinguishing feature is in those cases. I mean, for example, you could cook up some partition function or something, but yeah, I'm not entirely sure. Yeah, but the reason I believe is because the anyons condense the boundary does not fully specify the boundary.
Thanks.
Yeah.
But one more second, one second.
Yeah.
Then we know the classification of the SPTs will be given by some HF2 G
Yep, that's right.
1. Then do I know the mathematical structure that classifies this boundary will also be the same thing?
Yes, yes, yes. Indeed. So actually, this works for any for any discrete group G. So in the general case for a discrete group G, my bulk will be G kind of a G toric code or a G quantum double, and the gap boundaries of the G quantum double are in one-to-one correspondence with GSPTs. So the classification matches exactly in this case.
Yeah. Thanks.
Yeah. Okay, so I want to move on to gapless SPTs. And before talking about the SymTFT for them, which was worked out by in a paper by Rui and Drew Potter, I want to just briefly specify what what is meant by a gapless SPT in this context. So the idea is I want to consider a system which has a Z4 symmetry. So my full symmetry group is actually Z4, but this symmetry has the property that there exists a normal subgroup, which we'll call G gap, which has the property that it acts trivially on the low energy subspace. So anything that's charged under Z2 kind of will live in let's say, a highly excited state. So if G gap acts trivially on the low energy subspace, then what the low energy kind of degrees of freedom, what they actually see is the quotient of Z4 by Z2, which is this G low here. So G low, which is this quotient, is the symmetry of the low energy subspace. And one thing that's possible with this setting is that G low can be anomalous, even if G kind of is totally is non-anomalous or it's on site. And if this happens, if G low happens to be anomalous in this case, then the low energy description cannot be just trivial in a trivial gapped phase. So the setting that we're considering here, the low energy theory will be some gapless thing that's called the gapless SPT. Okay, so yeah, let me describe how this type of symmetry structure can be encoded in the SymTFT picture. So starting off, because we want to consider a system with Z4 symmetry, I want the kind of 2D topological order to be the Z4 toric code. And next, I want to encode this feature of having a Z2 subgroup which acts trivially on the low energy subspace. So to do that, I take my Z4 toric code, and in this kind of intermediate region, I condense anion E squared M squared. So I condense an E squared M squared in this region, and I obtain a new topological order, which is called the double semyon. And to see how the M squared acts, so M squared, the Z2 kind of subgroup is implemented by this M squared string operator. The reason M squared gets identified with 1 is that, for example, I can bring up an E squared from the bottom boundary, which we recall as the charge condensed boundary. I can bring up an E squared from the bottom boundary and then combine it with M squared and annihilate it at this domain wall. And so this is implementing the fact that M squared is 1 kind of when acting on the low energy degrees of freedom. And so I think the way to interpret it is that this Z4 Tor code is describing kind of the collection of all degrees of freedom in the system. And this region here is kind of describing the low energy subspace. And so this is saying that the M squared acts trivially on this low energy subspace. So next, I want to just kind of squish this middle region down to 0. And because I've condensed E squared M squared here, this turns into just a single boundary with E squared M squared condensed. And playing the same games as what we've been doing, we can identify what the set of string operators acting on this system, which act trivially on this, and translating this back to lattice model language, this becomes the string order parameter of the gapless SPT. And once again, we can notice that the endpoint of the string order parameter is itself charged under the symmetry operator. And so this is an example of fractionalization, again, in this context. What's interesting in this case is that actually this pattern of fractionalization with this string order parameter with the endpoint of this charge is actually, it's incompatible with being a gapped system. So this is what I alluded to in the introduction of how some types of fractionalization can only exist in settings beyond gapped faces. Okay, were there any questions about this example? I should mention that the Z4 gapless SPT is also, in a similar way, it's the paradigmatic example of a gapless SPT, in a similar way that the cluster state was the kind of canonical example of a gapped SPT. Okay, so let me now move to the sort of bulk of the talk, which is how to relate gapless SPTs to gapped SPTs, and a certain class of gapped SPTs. And this will sort of proceed just by a very kind of pictorial argument. So to start off, let me just consider like a quasi-infinite, a two-dimensional kind of region where I have start with some DG topological order, so a G gauge theory, and I condense some set of anyons in this middle region. And I do so such that there's a gap boundary between all of these things. So one thing I can imagine doing is kind of cutting this system in half and getting a picture that looks like this, which is very similar to what we saw in the previous case for Z4. So this should remind you of like a SymTFT picture for a gapless GSPT. Now, on the other hand, instead of cutting this system, we can fold it in half like a taco and obtain this kind of folded structure, which yeah, let me explain a little bit. So here we have DG and its orientation reversal, DG bar. And this intermediate region, we have this region where anyons are condensed. And at this fold here, I have a gapped boundary. And so based on this SymTFT picture, what I should think of this as is a SymTFT picture for a G times G gapped SPT, since I have a gap boundary here. So in some sense, I'm using the similar kind of construction to describe both the gapless SPT and the gapped SPT. Now, let's see what comes out of this construction when I apply it to this Z4 case discussed earlier. So just to reiterate the case from before, I started out with the Z4 toric code. In the middle region, I condensed E squared M squared. I obtained the double semyon. And if you work through sort of all the anyons that are condensed at each domain wall and at this boundary to vacuum, what you kind of observe is the following pattern of anyon condensation. So again, kind of by fiat at the bottom boundary, I've imposed the symmetry boundary condition, so all of the charges are condensed. And by working through which anyons are condensed, we obtain the following subgroup of anyons. So let me just go through this one by one. So the E squared A, M squared A is sort of the E squared M squared that I condensed at this boundary. And similar for this E squared B, M squared B, it's the E squared as M squared anyon that I condensed on the bottom half. But in addition to these two, I also have E squared A, E squared B, and I also have this this kind of anion EM on the A and E cubed M on the B. Now, because I've condensed this E squared M squared, and because I've condensed E squared, this when I condense charges, this naturally leads to spontaneous symmetry breaking. And you can check that the symmetry is spontaneously broken to a Z4 times Z2 subgroup. And in particular, it's a Z4 diagonal times a Z2 kind of anti-diagonal, which just means the Z2 kind of acts only on one layer.
So this can be checked just by looking at which local order parameters have no correlation.
Ah, good. Yeah, so for example, E squared A, E squared B has long range correlation.
Mm-hmm.
And E squared is neutral under the diagonal Z4 and the anti-diagonal Z2.
I see. I have a general question about the last page.
Yeah.
In the last page, you have the cut and the tackle.
Yeah.
In the cut part, do we necessarily get a gapless GSPT, or do we require additional condition to get a gapless SPT?
So it depends on how strict of a definition you want to give to gapless SPT. I think, yeah, okay. I think you always get a gapless GSPT under a sufficiently broad definition, but some of them, depending on what anions A are condensed, they may be trivial. They may be, yeah, they may be in a sense trivial, I think. In the sense that Rui described in his talk, actually. Yeah.
But is it correct that in all cases it's always gapless?
So the gapless is if I sort of don't, it depends on, you need to specify actually what happens at this boundary. So if I condense some anions at this boundary, it won't be gapless. But in the picture I've drawn, I've sort of implicitly condensed 0 anions at this boundary, and then it will be gapless.
Okay.
Yeah.
Thanks.
Right. So the conclusion is if I take the Z4 toric code, condense E squared M squared in the middle, and I do this folding, I get a non-trivial Z2 times Z4 SPT. Or I get a Z4 times Z4, which spontaneously breaks down to Z2 times Z4, and a SPT under the residual subgroup. Okay, so let me just go over the kind of fractionalization pattern associated to this Z2 times Z4 SPT. So in addition to actually, yeah, let me just start. So this first one should look kind of familiar just from the Z4 gapless SPT. It's this E squared M squared string order parameter, but on just one of the layers. And of course, I could have this on the other layer as well. So this kind of fractionalization pattern was inherited from the Z4 gapless SPT kind of directly. But I also kind of got this other type of fractionalization, which leads to a different kind of string order parameter, having long range order, given by because of this EM E cubed M anion that was condensed on the boundary. So yeah, the actual details of this is not actually that important. What I just want to draw people's attention to is the fact that the first string order parameter looks identical to the original one in the Z4 SPT. So one way of saying it is that I took the fractionalization of the gapless SPT and it was preserved while gapping out the system. And so, I mentioned earlier how this type of fractionalization should not be possible in a gap system, but there's no contradiction because actually, I've enlarged the symmetry group and so the presence of this extra symmetry together with this extra string order parameter allows everything to be consistent still. Okay, so this was an example of, I took the canonical or I took the canonical Z4 gapless SPT. I kind of did this folding construction, and I got a SPT that's not exactly the simplest kind of SPT. And one might wonder why that's the case. So it turns out, as one might expect, if I want to construct SPTs in this way, it turns out that you can't actually get all possible gapped SPTs in this way. Or another way of saying is that there are some gapped SPTs that are not in the image of this map. And so one would like to have some constraints on what kinds of SPTs can arise from this construction. So we might just call these kinds of SPTs folded SPTs. So one way of arriving at such a constraint is by defining this so-called W matrix. This is like a tunneling matrix that was introduced by these authors. So we'll define this tunneling matrix to just be the following. If I have an anion A in DG and it can tunnel through this system and become an anion alpha in DG in this condensed system, then I'll define WA alpha to be 1. And if this type of thing is not possible, if A does not turn into alpha, then it's 0. Okay, so this matrix kind of encapsulates the kind of tunneling that's allowed in between these two systems. I should say, strictly speaking, now I'm assuming that G is abelian for simplicity. In the general case, this would be the multiplicity of the tunneling. Okay, and in this folded picture, I want to define a different matrix. One might call this a condensation matrix. So I'll define this M A B bar to be 1 if A1 B2 bar is condensed at this top boundary, and 0 if not. And so this is basically just telling me which anions are condensed at the top boundary. And again, for simplicity, let me just assume that everything is abelian. So the characteristic feature of this folded boundary is that if I restrict my attention to this middle region, this region where I've condensed some anions, the condensation matrix in terms of these anions is simply a delta function. So something is condensed here if and only if it's condensed together with its inverse. But this is in terms of the alpha anions, and I would like to express this in terms of the A and B anions living in DG. And to do that, that's what I use the W matrix for. And so in order to get an anion alpha, I start with A and tunnel into alpha. I want to start with B bar and tunnel into beta bar. And I combine them using this condensation matrix, this delta function, which tells me that I'm restricting to this folded class. And when I do that, I can realize I can rewrite my matrix as a product of W and its transpose. And what that means is that the only possible condensation matrices that I can get from this construction are those that are symmetric and positive. So that's what puts the constraint, that's the type of constraint that this folding picture, this folding procedure gives on the possible SPTs. And it's possible to check that, for example, for the canonical, the Z2 times Z2 cluster state SPT, the condensation matrix, the corresponding condensation matrix, it's symmetric, but it's not positive. And so it won't be in the image of this construction. Okay, so the symmetry and positivity should remind you about density matrices. And that's the type of thing, that's exactly what we'll turn to next. There's no questions. Okay, so let me just make a brief aside onto mixed states, and I'll talk about mixed state topological orders and mixed state SPTs very briefly. So let me introduce this mixed state topological order. So imagine I had a pure state describing some topological order given by DG. Some pure state psi. If I want to represent its density, represent this state as a density matrix, one way of representing it is by taking DG and its kind of complex conjugate and considering those two as a single system. That's to describe the Bra and Ket, to make the Bra and Ket Hilbert spaces kind of their own thing. So this density matrix can be viewed as a state in the doubled, Bra and Ket Hilbert space, and the state is going to be described by dg times dg bar. And the utility of describing things in this way is that decoherence in a mixed state, in a mixed state topological order, has a simple interpretation. So if I'm handed a DG topological order, but someone made some measurements without telling me, that's like applying a quantum channel to my state. But certain kinds of quantum channels, if they involve, for example, measuring and forgetting or some kind of maximal decoherence, what this corresponds to is a condensation of AA bar anyons in dg times dg bar. So this kind of doubled state picture lets you think about decoherence and mixed state topological orders as just sort of the more familiar anyon condensation process.
Question?
Yeah.
Is this a fully general and precise statement?
Yeah, let me think. So I think the precise statement I can make is in the case of maximal decoherence, if I choose some certain operators in my and I apply maximal decoherence, that will correspond to condensation of certain anyons that kind of mix the Bra and Ket space. So it'll be like these AA bar type anyons. Yeah, for example, I don't want to say like any type of channel will always condense these types of anyons. That won't be true. But I think there is a precise statement for maximal decoherence.
Maximal decoherence meaning completely depolarization channel?
For example, yeah.
Mm.
Yeah. So like for example, 1/2 probability of applying X on a link and 1/2 probability of applying nothing, for example. That will condense some anyons in a toric code.
But how do I know this is model independent? Suppose it seems the description you just give relies on some picture of some solvable models as the starting point.
Yes.
But if the models are perturbed, how do I know it still works?
Yeah, I think I can only give you an argument based on the fact that these states are robust to local, like small local perturbations. Yeah. I think strictly speaking, maybe the most precise statement is only in these fixed point models.
Mhm.
But I think it's still, I mean, it is certainly still expected to be true slightly away. Because even after decoherence, the models still retain some kind of robustness to local perturbations, depending on which anyons are decoherent and so on like that.
Yeah. Yeah, I think it may be good to make the really general and the precise statement. Maybe if one can consider, suppose our initial state is some evolved version of the fixed point. By evolved version, I mean applying something like a finite depth quantum circuit to the state.
Yeah.
And then these channels will also be under. I can then go to the Heisenberg picture. The channels will also be mapped into some other channels.
Yeah, that's right.
And then I should ask whether the mapped channels can be further mapped into the mapped versions of the annual condensations.
Yeah, that's right. Yeah, I would say hard away from the fixed point, it's hard to make. Yeah, I think it's hard to make more precise statements. Although I certainly think it should be possible.
Yeah, thanks.
Yeah, thanks for the question. Let me now talk about symmetries in mixed states in preparation for understanding mixed state SPTs. So symmetries will come in two varieties. There's this strong symmetry and weak symmetry. Strong symmetry, I act with a symmetry operator only on one side of the density matrix, which seems unnatural. But okay. And for a weak symmetry, these are more familiar. I conjugate my density matrix by the symmetry operator, and if it remains invariant, I have the weak symmetry. So the first thing to notice is that if I have a strong symmetry, something that satisfies this, I automatically have a weak symmetry. Okay, but a strong symmetry obviously is stronger. The difference is that if I view rho as an ensemble of pure states, a weak symmetry implies that the ensemble as a whole is invariant under the action of the symmetry. But a strong symmetry would mean that this ensemble of states, the every state in the ensemble is invariant under the symmetry. Okay, so the strong symmetry is a stronger notion. And how it acts sort of in this doubled space picture is if I have a strong symmetry, it'll only act on sort of one layer in this picture. And on the other hand, if I have a weak symmetry, it'll act V and V dagger on the bra and ket space together. Okay, so yeah, I want to come to sort of the punchline of the talk, which is that actually it turns out that the folded SPTs, you can equally think of them as mixed state SPTs. And the reason is that so yeah, I should say, in this doubled space picture of thinking about things, density matrices will map to some subset of states in kind of this doubled Hilbert space. But it's a little bit tricky to figure out exactly which states, if I'm handed a state in this doubled space, how do I know it's a valid density matrix? So there are constraints that come from symmetry and positivity that tell me when, a state in this doubled space is actually a real density matrix. And it turns out that those constraints can be kind of precisely mapped to this constraint that arose when we were thinking about folded SPTs. And this shouldn't come as too much of a surprise because when we found folded SPTs, we found that this condensation matrix is symmetric and positive, and it's very similar to how density matrices are symmetric and positive. So you can find a sort of detailed explanation for why these two things are kind of precisely equivalent, at least in the abelian case. That's the case that we proved in our paper. But we sort of conjecture that it should be true more generally. Okay, so using this correspondence, let me just mention something about our understanding of mixed state SPTs before talking about the SymTFT. So the symmetry structure is very similar to that of gapless SPTs. I'll have a full symmetry group, which kind of is the symmetry group that can act on my degrees of freedom. And as a normal subgroup, I have a strong symmetry. So just mirroring the Z4 case from before, I'll take a Z2 subgroup of this to be a strong symmetry. And then the quotient of this will be this weak symmetry. I put weak in quotes because actually many people will use weak to refer to something slightly different, but morally this is the weak symmetry in the theory. Okay, and we can see that this exactly parallels the symmetry structure of the gapless SPT. And so indeed, what we can do is we can take the folding picture from before, and what we find is that this thing will kind of accurately describe the mixed state SPT in this case. So just taking the picture from before and reinterpreting as a mixed state, I have E plus and E minus E squared, M squared on both layers, and I have E squared on sort of in between the layers. And okay, there's a typo here. This should be E minus cubed. But anyway, it's the same pattern of condensation that we saw earlier. So now this leads to string order parameters. The kind of interesting thing is that, interesting or maybe disappointing thing is that for one of the string order parameters, this maps to the one that's directly inherited from the Z4 gapless SPT. This leads to a string order parameter that you can measure, for example, in an experiment, and and you can kind of you can diagnose this SPT this way. The other string order parameter is actually it's actually one of these Renyi 2 type string order parameters. And so this will be much harder to diagnose in an experiment. But these are precisely the types of string order parameters that would characterize a mixed state SPT. Okay, I went a little bit fast on here, but are there any questions about the mixed states SPTs and SymTFT? Okay, yeah, in the remaining time, let me just really quickly go over how we can use the SymTFT to make predictions, so to speak, about weak gauging. Okay, so I'd like to talk about gauging symmetries from the perspective of SymTFT. So, for example, let me consider a Z2 times Z2 SPT. Sorry, a system with a Z2 times Z2 symmetry. So on the symmetry boundary, I've condensed the charges, and I've left the dynamical boundary unspecified for now. So the thing that I would like to do is to gauge the diagonal Z2 symmetry. And the SymTFT gives a prescription for how to do this. It involves changing the symmetry boundary to be something else. So here I've changed the symmetry boundary to be a different pattern of anion condensation. So I've condensed MAMB and EAEB. This is like the diagonal condensation. And the general prescription goes in the following way. If I want to gauge a subgroup H, I want to modify the symmetry boundary to be the boundary that would correspond to the H preserving boundary. So if for example, I moved this MAMB, EAEB, if I moved this to the dynamical boundary on the left-hand side, I would find that this corresponds to SSB to the diagonal subgroup. Okay, so that's the prescription for how to do this gauging. When I gauged, there's also a procedure to identify what how the symmetry operators transform after gauging. So before gauging, my symmetry operators were MA and MB. After gauging, you can check that MA and MB become identified. And I have a new kind of symmetry operator, which is EA, which is identified with EB. Okay, and the procedure to do this is to identify which lines are confined at the symmetry boundary. Okay, and so once I do this, I get a new theory. It's still a Z2 times Z2 symmetric theory, but now, if I fix a dynamical boundary and I perform this gauging, in general, I'll map this to a different phase of matter. Okay, so how does this relate to gauging weak symmetries? So, well, if we recall, weak symmetries are the ones that act on both the bra and the ket simultaneously. And so this is exactly just like gauging the diagonal Z2 symmetry of the previous case. So here I have a Z2 and it's Z2 bar, but I can think of this as being like a Z2 times Z2 symmetry. And now I want to gauge the diagonal symmetry, which is the weak symmetry. And to do that, I change the dynamical boundary to this pattern of anions. So it's E plus E minus and M plus M minus, just like before. But in this case, something kind of strange happens. It's what I'll call a mixed state anomaly in quotes. And the reason that it's anomalous in quotes is the following. No matter what kind of gapped boundary I pick for the dynamical boundary, so in this case, there's three possibilities. There's E plus and E minus are separately condensed. There's M plus and M minus separately condensed, and there's E plus E minus, M plus M minus. And for those of you who are very quick, you might have already realized that there's something missing here. It's E plus M minus and E minus M plus, corresponding to what would have been the cluster state. But that's precisely the type of boundary that's ruled out by positivity in this mixed state setting. So actually, these are the only boundaries that are available. And you can check actually that all of these boundaries, they break the symmetry in the sense that I can always find a local order parameter that tunnels something from the top boundary to the bottom boundary. So all of these gap boundaries will break the symmetry. In the language that was introduced by Carolyn and Clay, there's no magnetic Lagrangian subgroup that's also consistent with positivity in this case. So it's a little bit curious. It seems like it's an anomaly that's, well, one, it's in this weird setting after I gauge this weak symmetry, but it seems possible in the context of mixed states where this positivity is in force. Okay, so that's actually all I have. To just summarize, we've developed this SymTFT picture relating gapless SPTs to gapped SPTs. This was this folding construction. And we've also found that this SymTFT for these systems applies sort of out of the box to mixed state SPTs. Yeah, some kind of future work that we're thinking about is, for example, can we do this weak gauging on the lattice? Can we do it in a Keldysh field theory? And how can we see this? Is it possible to see this mixed state anomaly, kind of diagnose it directly on the lattice? And are there kind of other ways of saturating this mixed state anomaly with some funny kind of mixed state phase transition or something of that sort? These are some things that we're looking into now. So yeah, thanks for everybody for listening.
Thank you very much, Marvin, for the very interesting talk. Any further questions? Maybe let me ask you, what do you mean by other ways of saturating the mixed state anomaly?
So in this, oh sorry, I need to. Yeah, in this previous slide, I've gave gapped boundaries that could saturate the anomaly. So all of these gap boundaries are symmetry breaking. Yeah. I mean, so one kind of clear choice that's possible is I just condense nothing. So this would be as if I took the Ising CFT and I gauged the weak symmetry. And certainly that's something that's possible. Yeah, I don't exactly know what that looks like either. But yeah, I mean, one might imagine that there's some kind of states that are kind of only available in this setting.
Does it make sense to gauge the strong symmetry?
So gauging strong symmetry is what we would normally call gauging symmetry.
Oh,
Yeah.
Any other questions?
Yeah, I have maybe two basic questions.
Yeah, please.
So the first one is about in this definition of gapless SPT, is it guaranteed that we have CFT descriptions for these SPTs?
Yeah, great question. The answer is no. So let's see. Yeah, so in this kind of setting that I've described here, actually, I'm not sharing, am I? Yeah, in this setting of gapless SPT, only in this symmetry structure, basically the only thing that's specified is kind of the fractionalization, actually. So it's like the kind of topological part of the symmetry that's fractionalized. So in no way is there guaranteed to be a CFT at low energies. That's a dynamical question, which is separate from sort of the kinematic data of what the symmetry is doing. Yeah, in many cases, certainly in all of these like paradigmatic examples that people consider, that there does happen to be a CFT at low energies.
I see.
Yeah, that's one might say that's a drawback of the SymTFT approach for gapless systems. So for gap systems, there's a sense in which the SymTFT actually tells you all of the universal data. So the order parameters, the ground state degeneracy, all of this is encoded by the gapless SPT. Sorry, all of this is encoded in the SymTFT. In the gapless case, there's extra kind of dynamical data that is also universal, but is invisible to the bulk. Yeah, there's extra data besides what anyons are condensed and so on.
So you mean that these extra data are not captured by the SymTFT? Is it correct?
It's not captured by, let me say it's not captured by this version of the SymTFT.
This
So
version
I know there's a series of papers by Liang Kong, I believe, where he kind of takes the CFT data and yeah, it does a boundary to bulk kind of correspondence using that. It's certainly more involved, and there's more data essentially than just what anyons are condensed at the boundary.
I see. Thank you. And this also answers my second question.
Okay,
My second question is about whether this gapless SPT should be anomalous, because we know that the gapless boundary of topological order have anomaly inflow, and I was
yes.
wondering if it is bounded to be anomalous. Then you
Yes,
just
yes.
answered that the answer is no, right?
The answer is no. So like a trivial gapless SPT would have no anomaly,
Yeah,
but
I
like
see.
a non-trivial gapless SPT would have an emergent anomaly.
I see. So I mean, whether the gapless is anomalous is not strongly bonded to the bulk. I mean, it's not strongly bonded to the bulk property, because you just said there are extra data that are not captured by
So the anion condensation. Okay, if we're sticking to the Beeline case, the anion condensation is enough to determine the anomaly.
Yeah,
But it's not enough to determine it's because the anomaly is still kinematic data. It's data about the symmetry and how it acts. But it's not enough to determine what CFT is compatible with this data.
Okay. See, thank you.
Yeah. Thanks for the question.
Any further questions? Okay, if not, I'll thank Marvin again for the very interesting talk. I think from your talk, I understand SymTFT more than the previous talks I attended.
I see. Thanks. Yeah.
Yeah, I
Happy to-
agree with that.
Yeah, thanks. Bye.
Yeah, thanks. Bye-bye.
Recording stopped.